So basically, Zener diode is a silicon PN junction semiconductor device which generally operates in reverse breakdown region. The Zener diode is fabricated with precise breakdown voltages by controlling the doping level impurity adding into it during the manufacturing process. The Zener diode has a breakdown voltage range from 3 volts to 200 volts. In 1934, a physicist Carl Zener investigated this breakdown phenomena in the PN junction diode and hence the name Zener diode. Right? So, Zener diode is nothing but a semiconductor diode. It is a semiconductor PN junction diode which generally operates in reverse breakdown region. And these are manufactured using a precise breakdown voltages by controlling the doping impurities added to it during the manufacturing process. And the breakdown voltage range is in between 3 volts to 200 volts. And in 1934, a physicist called Carl Zener investigated this breakdown phenomena in the Zener diode. Okay, hence the name it is Zener diode. So I'll be drawing the symbol of the Zener diode. Just look at it, all of you. So this is the Zener diode symbol having cathode and anode. Having cathode and anode. It's a symbol of the Zener diode. Next, let me draw the forward biasing of the diode circuit. So this is a battery supplying the voltage. This is the R. It is known as current limiting resistor. And this is the Zener diode. Okay. So this is about the forward biasing. Next, I'll be drawing a circuit with related to a reverse biasing of the diode. This is a current limiting resistor R. So diode is placed in a opposite direction. You can see this. Hence the battery is connected in the reverse way. Hence it is a reverse biasing. Reverse biasing. So I have told here the Zener diode operates in reverse breakdown region and its breakdown voltage ranges from 3 volts to 200 volts. A physicist known as Carl Zener invented the breakdown mechanism in Zener diode, hence the name Zener diode. So here this is a two-terminal Zener diode, anode and a cathode. So here the positive terminal of the battery is connected to the positive P type of the Zener diode and the negative terminal is connected to the N type of the Zener diode. Hence it is forward biasing. Biasing means connecting an external DC voltage to the device. Here the positive terminal of the battery is connected to the N type and the negative terminal is connected to the P type of the Zener diode. Hence it is reverse biasing. So this shows the symbol of the Zener diode, and the DC voltage is applied to the Zener diode so that it makes it forward biased, and also the battery is connected to the Zener diode in the opposite direction, hence it makes it in the reverse biasing diode. Next we have characteristics of the Zener diode. So characteristics of Zener diode. Normally this characteristics I am drawing now. This is forward, this is reverse. This is a characteristics with current IF and the VF voltage. This is known as forward bias, and this is known as reverse bias because the voltage is negative and the current also flows negative, hence it operates in third quadrant, reverse bias region, and this is forward bias region. So here we have a breakdown voltage VBR, it stands for breakdown voltage, and cut-in voltage is 0.7 volts. After the 0.7 volt the current starts increasing exponentially. So here you can see the characteristics of normal diode, operating regions, and the characteristics of the normal diode. So here this portion we can see the shaded area, and this portion we can see forward and the reverse. This is the characteristics of the normal diode. Let me draw the characteristics of the Zener diode now, and let me tell you what is the difference. So on the y-axis always it is a current, on the x-axis it is a voltage. So here we have the Zener operates like this. The Zener operates always in the reverse characteristics. So this point is known as VZ. It is known as breakdown occurs here. BZ. So this portion it operates. I'll just draw it in the shaded area. The Zener diode operates here in this region, reverse breakdown region it is. This operates in the reverse breakdown region. So here it is reverse voltage applied, and here the reverse current is flowing. So when you apply a reverse voltage, a reverse current flows at this point VZ, breakdown voltage. Whenever the reverse voltage applied increases than this point, okay, suddenly the current exponentially it starts increase. At that point it is known as breakdown voltage. It is known as reverse breakdown voltage. This point, at this point the current starts suddenly increasing exponentially. At this point of voltage it is known as reverse breakdown voltage. When you apply a reverse voltage, reverse current flows. So this is the operating region. Shaded I have shown here, shaded for Zener diode. So normal diodes operate in forward bias region as well as in the reverse bias region, whereas Zener diode operates only in the third quadrant, that is in the reverse bias region. When you apply negative voltage, negative current flows. So negative it is in the third quadrant. Hence this is a difference between the normal diode and the Zener diode. So normal diodes operate as well as in this, see you can see here, no, forward bias, reverse bias. But this Zener diode Zener diode is designed to operate in the reverse bias condition only. So in the reverse biased condition, the diode carries reverse saturation current till the reverse voltage applied is less than the breakdown voltage. Okay, so reverse breakdown. So what is this? VR, I'll just tell you. VR is reverse voltage. The voltage we have applied. Okay, so VZ is breakdown reverse voltage. Breakdown reverse voltage. As I have already told you, normal diodes operate in forward as well as reverse region, bias region, whereas Zener diode operates only in the reverse biased condition. So in reverse bias condition, the diode carries reverse current. So in reverse bias condition, the diode carries reverse current. IR is known as reverse current. In the reverse bias condition, the diode carries reverse saturation current till the reverse voltage applied is less than the reverse breakdown voltage. But another condition, when the reverse voltage applied is greater than the reverse breakdown voltage, the current through it changes drastically. This point. When the applied VR is greater than the reverse breakdown voltage, the current through it changes drastically, but the voltage across it remains almost constant. You can see here the voltage remains constant, whereas the current changes drastically. Such a breakdown region is a normal operating region for the Zener diode. I have told you this Zener operates in this. So whenever the applied voltage is a reverse voltage, is less than the breakdown voltage, the reverse saturation current flows. A very small reverse saturation current flows. Whereas when the reverse voltage applied is greater than the breakdown voltage, there is a sudden change in the current, and that point is known as reverse breakdown voltage. But the voltage is always constant, whereas there is a drastic change in the current, and this is a normal operating region for the reverse diode. So here the breakdown characteristics of the diode is very important, and it is shown in the operating region. Here I have shaded, and this is known as the operating region. So when the reverse voltage applied to the Zener diode is increased, reverse voltage is VR. When it is increased, reverse voltage applied to the diode is increased. Initially here at this point, a very small current flows in the amount of microamps. Initially when I apply the reverse voltage now, a very small current flows in the amount of microamps or even less. This is known as reverse leakage current of the diode, and hence it is known as I0. Reverse leakage current, and it is known as I0. At a certain reverse voltage, current through the Zener diode increases rapidly. You can see here, after certain voltage is increased, current increases rapidly. So this change from a low value to a large value of the current is very sharp. It is marked here, it is very sharp. The change of the current value from low value to a high value, that is, high value is a large value of the current, is very sharp, and it is very well defined here in the graph. Such a sharp range in the reverse characteristics is called knee. It is called knee voltage. Here at this point, when the current value increases from a low value to the large value, such a drastic change in the current, that particular point, sharp change in the reverse characteristics, is known as a knee, or it is also known as Zener knee. Zener knee of the curve. Zener knee of the curve. At this knee, the breakdown is said to occur. At this point, it is known as breakdown. I have written here. At this knee voltage, breakdown is said to occur in the device. And the reverse bias voltage at which the breakdown occurs is called Zener breakdown voltage. This point. Zener breakdown voltage. The reverse bias, this VR is there, no? The reverse bias voltage at which point the breakdown occurs is known as Zener breakdown voltage. So this point is known as reverse breakdown voltage. So this is known as Zener breakdown voltage. So this is the normal difference between this Zener diode and the normal diode. Normal diode operates in forward as well as reverse bias region. The Zener diode operates only in the reverse bias region. Okay, as long as you apply the VR reverse voltage, a small amount of current flows, and as and when the voltage increases, VR is greater than the VZ here. Okay, the current, there is a sudden change in the current, whereas the voltage remains constant, and that point is known as a knee. And voltage at which the reverse voltage at which the breakdown occurs is known as Zener breakdown voltage. It is known as VZ. Zener breakdown voltage is known as VZ. So next we have VI characteristics of the diode, Zener diode. So I am drawing the complete VI characteristics of the diode. Okay, so here we have current, here we have voltage. This is the forward characteristics. This is the origin point 0, right? And we have here a small current in this way. It should go like this. A small current will flow here. Yes, this is a curve of the reverse characteristics of the. So this is I naught. Okay, at this point it is known as IZ min, or it is also known as IZK. This point, as we all know, it is known as knee. Okay, so this is VR, and this point VZ, breakdown voltage, reverse breakdown voltage of the Zener diode. Okay, so here this particular point, it is known as Zener region. So in between some mark, it is the IZT, and here IZ max, or we call it as IZM. So this is the complete VI characteristics. So here is the VI characteristics of Zener diode. So this is a complete VI characteristics of the Zener diode. So the maximum current at Zener diode can carry safely is called Zener maximum current. Zener maximum current. So these are some terminologies, you should know it. So maximum current a Zener diode can carry safely is called Zener maximum current, and it is denoted as IZM, or it is denoted as IZ max. So in practically circuits, to limit the Zener current between IZ min and IZ max, a current limiter resistor is used in series with the Zener diode. Okay. The current at which the nominal Zener breakdown voltage is specified is called Zener test current. So what is IZT? The terminology IZT. The current at which nominal Zener breakdown voltage is specified is known as Zener test current IZT. So the Zener breakdown here almost remains constant. Here you can see at the VZ point the almost voltage remains constant. And the power dissipation here, PZ is equal to P into VI, you know it, no? VZ into IZ. So the power dissipation PZ is equal to VZ into IZ. So this is the complete VI characteristics of the Zener diode. Here you need to tell about the reverse characteristics, IZ min, IZT, the minimum current and the maximum current. So minimum current which the Zener diode can carry is the Zener minimum current. The maximum current that the diode can carry safely is known as Zener maximum current. And IZT is the current at which the Zener breakdown voltage is specified, is called Zener test current. So these three terminologies you need to write when VI characteristics of diode is asked. Next, equivalent circuit of Zener diode. So it is equivalent to a battery, equivalent to a battery VZ. So ideal equivalent circuit of Zener diode. So students, when the breakdown occurs, then IZ may increase from IZ minimum to IZ max, but voltage across the Zener remains constant. So here, when the breakdown occurs, the current increases, but the voltage essentially remains constant. Hence actually the internal Zener impedance decreases as the current increases in the Zener region. But this impedance is very small. Hence ideally the Zener diode is indicated by a battery of voltage VZ. Okay. So we have a term known as dynamic resistance here. So the dynamic resistance is defined by a formula, ZZ is equal to delta VZ divided by delta IZ, that is equal to 1 divided by delta IZ divided by delta VZ, that is equal to 1 divided by slope of reverse characteristics in Zener region. So all of you note down this. Dynamic resistance, very important parameter, is equal to V by I, V Z divided delta VZ. Delta VZ is a change in voltage and a small change in the current. That is equal to impedance 1 divided by this. You will get the impedance, the slope of reverse characteristics in Zener diode. Okay. So this is about the dynamic resistance. Zener has a small resistance inside it. So in the Zener region, this resistance is called dynamic resistance and it is known as Z, and a small z. Practically this is not exactly what the small change in the Zener delta IZ produces a small change in the Zener voltage. If current changes, then voltage also changes. So the ratio of delta VZ to delta IZ is called Zener resistance. Okay. So this is about the equivalent circuit of the Zener diode. So here Zener power dissipation. Zener power dissipation, that every diode or a Zener diode has a capacity to dissipate certain power. When it is operating, no, some power will be dissipated. So this capacity is expressed in the maximum DC power rating. So here a simple expression is there, power dissipation is equal to Vz into Iz. This one you remember, this expression. That is nothing but P is equal to Vi. So power dissipation, D stands for dissipation. Power dissipation of the Zener diode is equal to Vz into Iz. So Zener power dissipation. This expression you remember, it will be used in the next. So breakdown mechanisms. Breakdown mechanisms in Zener diode. So the breakdown mechanism. So there are two different mechanisms. Due to which the breakdown may occur in the Zener diode. So one is Zener breakdown. Second one is Avalanche breakdown. So for these Zener diode, most suitable commercially available are silicon diodes. Silicon diodes. Maximum value of the voltage breakdown by the Zener mechanism is low, that is between 5 volt to 8 volt. So consequently the Zener breakdown occurs less than 6 volts. Avalanche breakdown occurs when the voltage is greater than 6 volts. So for Zener diodes usually we use the material silicon. Okay.
Silicon.
Yes, what? So whenever I apply a reverse voltage of 6 volts or less, there creates a field across the depletion region. So at the PN junction, at the order of 3 into 10 raised to 5 volt per centimeter. So an electric field of such high magnitude has a large force on electrons. So this electric field creates a large force on valence electrons, tending them to separate from the nuclei. Separating from the nucleus means what? Breaking the covalent bonds. So when such electric field intensity becomes more than, or when the electric field becomes more than 3 into 10 raised to 5 volt per centimeter, the time electron hole pairs are generated in large numbers, and hence there is a large increase in the current observed. If suppose there is a current limiting resistor, to prevent the large current to increase it to a higher value, the diode may be destroyed. If resistance is not that much able to control the value of the high current value, then the diode may be destroyed because of the excessive heating at the junction. So in Zener breakdown, the value of the breakdown voltage decreases as the PN junction temperature increases. So thus such diodes are having negative temperature coefficient. Second one is avalanche. Avalanche breakdown. So in this avalanche breakdown, we apply the reverse bias. It causes when you apply a small voltage, a small current flows. When I apply a small small reverse bias voltage causes a small reverse current flow in the device. This is due to why? Why? Because of the movement of the minority charge particles. That is, minority charge particles are electrons from the p material and holes from the n material. So this polarity of reverse bias voltage is such that only the minority charge particles are able to cross the p-n junction, while the majority charge particles move away from the junction. As we have already seen, in the reverse region, the depletion region gets widened because the majority charge carriers move away from the junction and the minority carriers move towards the junction. As the applied reverse bias voltage becomes larger and larger, the minority charge carriers increases or it increases. Hence, collision between these particles and electrons are involved in the covalent bond of the structure. So, if the applied voltage is such that the traveling electrons do not have high velocity, then the collisions take some energy away from them, changing their velocity. If the applied voltage is increased, the velocity and hence the kinetic energy of electrons increases. If such an electron dashes against an electron involved in the covalent bond, then the collision gives bond valence electron enough energy to enable it to break the covalent bond. So when an electron dashes with the another electron in the covalent bond, this collision gives the electrons enough energy to enable it to break the covalent bond. So when the covalent bond is broken, one electron by another electron collision creates an electron hole pair. So what happens is multiple electron holes pairs are created. This phenomenon is known as carrier multiplication. Electron hole pairs are generated so quickly that in the such large number there is an apparent avalanche or a self-sustained multiplication process. At this junction, it is said to have breakdown and this current start increases rapidly. To limit such current, we have current limiting resistor that is very necessary, and this Zener diode have a Zener voltage above 6 volt in order to have the avalanche breakdown to occur. So we are studying about the photodiode. As per the quantum theory, light is in the form of photons. Light is in form of photons, and each photon delivers an energy packet, and photon delivers an energy packet to the surface wherever it falls, to the surface on which it falls. So quantum theory, according to the quantum theory, light is in the form of photons and each photon delivers an energy packet to the surface on which it falls. So it delivers an energy packet. So we have an expression for that. W is equal to hf joules. Joules is a in which we measure this quantum theory. So h is what? Planck's constant. It is a standard constant. Planck's constant. It is given as 6 into 6 to 4. Its value, standard value is 10 raised to minus 34 joules. F is frequency of light. Light waves in hertz. F is equal to V by lambda. V is velocity of light. Three into 10 raised to 8. Lambda is equal to wavelength in meters. Armstrong, we measure it is in Armstrong. It is Armstrong or micrometer. So 1 Armstrong is equal to 10 raised to minus 10. This is 10 raised to minus 10 meter, or 1 micrometer is equal to 10 raised to minus 6. This is 10. So this is a measurement. Okay, we have one formula for this photodiode. Okay, W is equal to HF joules. H is equal to Planck's constant 6.624 into 10 raised to minus 34 joules. F is equal to frequency of the light waves in hertz. F is equal to V by lambda. V is the velocity of the light, 3 into 10 raised to 8 meters per second. Lambda is equal to wavelength in meters. It is measured in Armstrong or micrometer. 1 Armstrong is equal to 10 raised to minus 10 meter, or 1 micrometer is equal to 10 raised to minus 6 meter. So intensity of the luminous flux, whenever you talk about the light, we have luminous flux incident on the unit area. So 1 luminous flux, I'll just write here, 1 luminous flux is equal to 1.496 into 10 raised to minus 10 watts. So let me talk about the function of the photodiode. So this was the expression of the photodiode. W is equal to HF joules. So here we have the photodiode. I'll just draw it. It is similarly a PN junction diode, photodiode, with a battery, with a current limiting resistor, so here we have some focusing lens. We have a characteristics here of the photodiode. It looks like this. So it starts from here actually, so I have deleted it. Say 0, 10, 20, 30. V lambda, or we call it as reverse voltage. Plus 200, 400, 600. I lambda is equal to micro amps. So here 100, 2000, 3000 values are there. So this is the characteristics of the photodiode. Voltage in the x-axis, current in the y-axis. So this is the IV characteristics. I'll just write here IV characteristics for various values of light intensity. So this is the VI characteristics. So let me explain the working first. We have seen the equation and we have seen the VI characteristics. Let me explain this now. So here, this is a photodiode actually. Photodiode is a PN junction. It may be made up of silicon or it may be made of GE or a germanium, which operates in the reverse bias region. So the photodiode is a PN junction which is made up of silicon or germanium, which operates in the reverse bias region. So the reverse saturation current, it is depicted as I lambda, which is microamps. Reverse saturation current I lambda microamps is limited. Okay, as light is made to impinge, this light, so light is made to impinge on the junction. This is a junction and this is a lens. Through this lens, light is made to focus on this junction. The light photons impart the energy to the valence electrons, causing more electron hole pairs to be released. As a result, the concentration of minority carriers increases, so does the current. So this much is the explanation. Photodiode is a PN junction. It operates in the reverse bias region. The reverse saturation current is I lambda, it is in microamps, is limited. As the light is made to impinge on the junction, the light photons are released and they impart the energy on the valence electrons, and more number of electron hole combinations are released, hence there is a constant increases in the current. So here they're talking about the VI characteristics. So VI characteristics of various values of light in the 100, 2000, 3000. There are various values of the light intensity. This is the voltage V lambda, reverse voltage. This is the I lambda, reverse saturation current measured in microamps. So here there are various values of the light intensity for the voltage across us, voltage in the x-axis, current in the y-axis. So as the current increases linearly here, okay, and this is known as, sometimes it is known as a dark current, corresponds to the light impinged. When the current flows due to the light impinging on this junction, the current flows, and that current is known as dark current. As the current increases almost linearly, you can see here, it almost increases linearly, and the photodiode germanium is more suitable for the construction of the photodiode. Okay, so this is about the photodiode.